Welcome back to the ETSI IQC Quantum Safe Cryptography Virtual Executive Conference. Our next session is an introduction to quantum safe cryptography for business and policy leaders. Joining me now from Ontario, Canada is Professor Michaeli Mosca. Michaeli is the co-founder of the Institute for Quantum Computing at the University of Waterloo and a founder of the ETSI IQC workshop series in quantum safe cryptography. A reminder to viewers that you can send in questions about this presentation or the summit in general, and we'll look to answer them during our live Q&A at the end of the day. There's a form to submit your questions here on the website. Welcome, Michaeli. Thanks for joining us today. Talk us through how quantum computing and quantum cryptography are enabling these fundamentally new capabilities.
Well, it's a pleasure to be here and to provide this introduction. Yes, first off, it's important to emphasize how profoundly different quantum computing is from other exciting and powerful computing technologies, such as cloud computing, supercomputers, neuromorphic computers, AI, and so on. Quantum computers exploit the so-called superposition principle, which is the ability to, in a meaningful way, embody exponentially many configurations at the same time, in a way that we don't believe is possible, in a way that we don't believe can be simulated by any classical computing platform without using an exponential amount of resources. That means any computing paradigm that uses only classical resources and is trying to simulate even a few hundred quantum bits, even if they're using all the known matter in the universe, they won't be able to perform that simulation. Now, the reverse isn't true. A few hundred quantum bits isn't more powerful than any classical computer for any computational problem, just for some computational problems. And so this leads to the natural question of which useful problems can be solved by quantum computers better than any classical computing platform. So quantum computers, as well as other quantum technologies, have this immense power that it could be tremendously impactful. Are you ready? Do you understand the known capabilities and how ready the technology are? Do you understand the impact of these capabilities on your organization or sector? Do you have a plan to benefit from the disruptions and the new capabilities? And importantly, do you have a plan to mitigate any quantum threats? Now, with any strategy, executing that strategy is 90% planning and 10% doing. And if it's showtime and you don't have that plan, you won't be able to call a timeout and make up for that lost time. So what are some of the known possibilities, some of the known advantages of quantum technology? There's a handful of areas where we believe quantum algorithms are much better than classical, such as the design of new materials or the simulation of chemical reactions at the quantum level, and certain other industrial optimization problems, perhaps even related to cyber defense. And there are non-computing applications as well. As with any truly new and novel and disruptive technology, I expect the largest impact will eventually be in applications we haven't even discovered yet. So the best known application where quantum computers vastly outperform classical ones is in a special kind of cyber attack. And to understand this threat and how quantum can be used to defend it, it's helpful to go through just some of the basic elements of how we use cryptography to protect ourselves against cyber attacks. How is it even possible that we trust our information and our systems to platforms we don't fully control, and in many cases we don't even trust? How is that even possible? How does HTTPS and how do VPNs allow us to do secure transactions through this untrusted medium? So I'll just quickly walk through three simple tools we use every day to achieve security through this untrusted environment. So think of a very simple scenario where there's one party, typically we'd call him Bob, who wishes to send some information to Alice through a medium where there may be adversaries who we call Eve, wishing to somehow, say, compromise the confidentiality of that information. Well, the way we do that today is if Alice and Bob share a secret random key K, right, they encrypt that message with that key, and the adversaries, the people in the untrusted part of the ecosystem, they only see the ciphertext, these random bits of information. And the intended adversary can decrypt that ciphertext and recover the information. So symmetric encryption is a really powerful tool that enables us to use these untrusted infrastructures. Of course, it's not enough, because how do Alice and Bob get those keys in the first place? So key establishment, or key agreement, or key exchange is another important primitive that we need every day in order to work in the current digital ecosystem. And lastly, how does Bob know the information is actually going to Alice? How does Alice know the information came from Bob and hasn't been tampered with? So we also need authentication. These are everyday tools we use in order to transact in today's world. And there's much, much more. I've just highlighted 3 very important tools that we use every day, but there's a whole new generation of applied cryptography that could be deployed to achieve even more in today's ecosystem. But I'm going to focus on those 3 for today's talk. So the quantum challenge comes in when we understand that many of these tools, they're only secure, their security is based on the difficulty of some mathematical problems, such as finding the factors of a large number. So in one direction, it's easy. If you give me 2 prime numbers, I can easily compute their product. But if I give you their product, it's believed to be infeasible to factor a very large number. However, a quantum computer, this happens to be one of those problems where quantum computers truly excel. Right? And they will factor these numbers and break the so-called RSA crypto systems very efficiently. And going to larger keys is not a plausible solution because the time to decrypt is comparable to the time to encrypt. So we really need a new way to do things. And it's important to emphasize that our entire digital ecosystem, our entire digital economy, which uses all sorts of platforms such as cloud computing, payment systems, the internet, and so on, these are secured by security protocols such as secure web browsing, auto updates, VPNs, and so on. And their security depends on the security of a small handful of cryptographic primitives, such as the RSA protocol I mentioned earlier. Quantum computing breaks essentially all the currently deployed public key algorithms that we depend on, which are primarily used to achieve key agreement and to achieve authentication and signatures on the internet, for example. These are essentially completely decimated by quantum computing attacks that will be available once we have large-scale quantum computers. Symmetric key cryptography, so encryption, for example, is weakened by a quantum computer, but we know that a larger key length will defend against the known quantum attacks. So that also needs to be handled. But the most worrisome part is replacing, somehow mitigating the problem that asymmetric cryptography or public key cryptography will be decimated. And it's important to emphasize because one can easily get overwhelmed with this flurry of this never-ending list of new cyber attacks. But they're all different. They're qualitatively different. And cryptanalysis is a cyber attack we haven't really faced in the modern era. And it's a very challenging one because it's foundational, it's systemic, it's used everywhere. And if the fundamental crypto is broken without a failover in place, we have a serious problem. Essentially, adversaries have the digital master key. So the usual cycle of reducing or protecting your systems as best you can, detecting as best you can, and then remediating, there's a serious problem now because we don't have tools with which to remediate. So I've laid out briefly what the challenge is, but of course, if quantum computers aren't here yet, and they're not likely here now, and they're not likely to be here in 6 months or in the very short term, so do we need to worry about this, or can we just wait and see? Well, and the answer depends. In many instances, of course, we cannot wait and see. How soon one needs to act depends on 3 key parameters, and this is essentially the fundamental equation of quantum risk management. The first question is, going over all your digital assets, all your information assets and the tools you use to protect them, you have to ask for any specific information asset, what's its shelf life? What's its security shelf life? Does it need to remain confidential for 10 years? 15 years? Let that be X. Secondly, looking at the systems you use to protect that information today, how long will it take you to migrate those systems to ones that will be resilient to quantum attacks? Is it 1 year, 5 years, 10 years, 20 years? It depends. But let's call that Y. So that's the time it would take you to migrate that system to a position where we believe it can't be compromised by quantum attacks. And lastly, when will the threat be real? When will adversaries have quantum computers in their hands and be able to compromise those systems and those information assets? Call that Z. Now note that for the next Y years, right, we are stuck with the current quantum vulnerable tools. We're supposed to have another X years of security, confidentiality, and integrity. But if X plus Y is greater than Z, then we're already too late. There's already losses that need to be minimized in the future. So one needs to do this assessment and see where there's losses, and we need to very quickly rush and put on a sort of Band-Aid to minimize those losses, and where there's still time, if X plus Y is less than Z, there's still time to take a more evolutionary migration lifecycle management approach. So to summarize, or maybe elaborate, this really implies 4 threats. I've already touched upon one. Information that is being communicated now and has been communicated in the past and is potentially being recorded by adversaries. If X plus Y is bigger than Z, that information could be decrypted and made available to adversaries. So that's the first, the record now, decrypt later attack we need to worry about. Of course, a much scarier problem is if Y is bigger than Z. If the systems are broken and we still don't have the failovers deployed, because then it's not just that some confidentiality and integrity might be compromised, but the systems themselves are no longer useful. Now, implicit here is if we try to rush, if we don't start soon enough, right? If we don't get all the building blocks in place, so we don't have all the planning done when it's showtime, and we end up rushing to try to quickly patch this, manage it as a crisis, that will inevitably lead to design flaws and implementation flaws. These are problems, these are vulnerabilities that can be exploited by classical attacks. You don't need a quantum computer to take advantage of these kinds of mistakes. So you're going to be vulnerable to conventional cyber attacks if you manage this as a crisis. And compatibility and interoperability are also at risk if not managed proactively. And lastly, loss of trust. If it becomes apparent to users and to society that our digital systems are not secure against these quantum attacks, as these quantum attacks become more and more real, they will start to lose trust in institutions and in the technologies that underpin our digital economy. And this can have all sorts of very negative consequences. So where are we? What is Z? How close are we to having a working quantum computer that could realistically threaten our digital economy? Well, this is no longer just a science experiment. When I would give these talks 10 years ago, I would show pictures of the state of the art, and it looked like a science experiment, and I'd have to explain how it really connected to a realistic quantum computer. Now we see a wide range of global players. In addition to academia, there's many large companies as well as small companies building platforms. They already have small prototypes and are in the process of scaling them up and improving their quality. So we see this all across North America, Europe, again, established players, new players entering the game. Our friends in Asia, China in particular, have made tremendous progress in the last few months, let alone the last few years, toward the implementation of a large-scale quantum computer. And furthermore, another signal that this isn't just a science experiment or something that's being done because of the challenge of it all. People are working on the full software stack to be able to leverage the capabilities offered by quantum computers to solve real-world business problems. Right? So there's everything from the software to run the computers, the software to optimize algorithms, and there's incubators set up to identify opportunities to leverage quantum advantage, and so on. Those great activities, again, accelerating tremendously in recent months and recent years. So this train is moving very quickly. And furthermore, we expect it will accelerate even further. At the present time, we see nations around the world doubling down on their quantum investments and trying to make sure they capture the biggest market share possible and also make sure they're not vulnerable to quantum threats. So if you want to know what is the next major milestone to indicate, because we don't have a large-scale quantum computer that can threaten these systems today. So of course we have to follow all the key milestones. Well, the most important milestone that is coming that will indicate tremendous progress towards a cryptographically relevant quantum computer is the achievement of a so-called fault-tolerant quantum bit, or a logical qubit. So if you think of bits today, you have an application, somebody writes some code, some software, it gets compiled down to send a sequence of pulses down to bits encoded in transistors. And these high-level algorithms get compiled down to very simple operations that flip a bit, do a NOT gate or an AND gate, very simple logic on 2 bits, such as a controlled NOT, which flips 1 bit depending on the state of the other bit. For a quantum computer to implement a controlled NOT, the well-defined path that many are pursuing is using so-called fault-tolerant quantum error correcting codes. And to achieve these fault-tolerant gates, you need a collection of dozens, if not hundreds, of these physical layer qubits. I have a picture here for us. So on this chip, this is a picture of an actual chip, you'll see 4 tiny loops. Those tiny loops encode a quantum bit, right? An amount of current going one way or another way. There's 2 distinguishable states in there, so we can encode a physical quantum bit, and those are 4 quantum bits. We need dozens or hundreds of those bits on a chip, and the red and blue lines indicate certain operations using those electrodes and other pulses to manipulate those physical layer bits to implement an algorithm that affects the desired operation, which in this case is a controlled NOT. And if you want hundreds of qubits and hundreds of controlled NOTs, you need hundreds of times of these physical layer qubits. This is what we're aiming toward. And if you follow the literature and the research closely, you'll realize people are building or working toward the building blocks of these fault-tolerant quantum error correcting codes. So this is a very important milestone to track. And in fact, just a few days ago, our friends at IBM revealed their roadmap and indicated that they expected to have a handful of such logical qubits by 2023. And our other friends at IonQ, for example, have recently announced some very nice results with a larger and improved platform where they're doing some of the building blocks of quantum error correction. So many serious players are moving toward and making real objective progress toward the realization of a fault-tolerant quantum bit. And I'll put here for your reference a couple of resources that help us track that one can look at to see in more detail all these difficult challenges, and it can follow them as they're being met. Right? And there's this nice one on the left here by our friends in Germany, translated in English. One nice aspect about this report is they update it regularly, so you can see where things are in a relatively up-to-date fashion. So the bottom line is, what is Z? Right? That's the question we want to know. So there's a lot of uncertainty, right? And of course, in the business world, you're constantly dealing with uncertainty, and that's just part of doing business. But we want to understand, when do we think this is realistically going to happen, right? So we look at, I've been following this for over 20 years, and in 1996, understanding all these different elements and seeing where the state of the art was, I estimated we are not going to have a cryptographically relevant quantum computer in 20 years from then. Of course, those 20 years have come and gone. And the chance of a cryptographically relevant quantum computer, in my estimate, went from 0% to 1% to now being 80%, right? And I think there's a very significant threat within 10 years, which I estimated about 20%. And I would estimate even the 5-year probability, while it's small, it's not completely negligible. And we surveyed, with the support of the Global Risk Institute, my team surveyed 22 thought leaders in this field who similarly had had many years of experience understanding all the different elements, following progress, and asked them, okay, all things considered now, when do you think we're going to have a cryptographically relevant quantum computer? Right? And you'll see the histogram of responses. And they vary, of course, but there's obviously patterns. Right? And we can see the likelihood heating up. So again, it's not completely negligible based on, again, 22 thought leaders. A significant handful of them placed the probability at greater than 1%. Okay? And again, for a critical system, a critical infrastructure, that is not something to completely ignore. And then the 10-year probability starts to become significant. and you start to see rough approaching 50% odds in the 15 to 20-year horizon, depending on who you ask. And we've rerun this survey, and we'll be publishing those results soon. And this year we've interviewed 44 thought leaders, and we'll have some additional new insights there. So that's the problem. That's our estimate. That's what we have to say. That's what I have to say about Z, the threat timeline. So what about Y? What about the migration? What can we do about this? Is there anything we can do? Is cryptography dead? Well, no. We believe we know how to fix this, right? And the straightforward alternative is to replace the mathematical codes we currently rely on, right? The current mathematical algorithms with other ones that are believed to be resilient to quantum attacks. That turns out to be very, very, very hard. Most things we try, mathematicians have tried, end up being very easy to break. But after decades of work, there's a small handful of alternative mathematical algorithms that we think can underpin our digital systems going forward. This is also known as post-quantum cryptography. But quantum technology, in addition to breaking the current tools and requiring us to replace them with some alternatives, offers some new tools. So we can not only reestablish a status quo, but we can actually add new tools to the ecosystem and make it even stronger than it was before. And these tools work well together. One doesn't have to decide which one's better. This is not an either-or situation. We reestablish a status quo with new mathematical algorithms, and we enhance it further with new quantum cryptographic tools. So for example, quantum, apart from giving us computational power that poses a threat to our cryptographic systems, offers us, for example, a way to generate random bits. It's arguably, I think most scientists would agree, the only fundamental source of randomness in terms of generating new randomness. So that's a powerful new opportunity. It has many advantages, such as, again, the ability to generate fresh randomness, and for certain sort of enhanced quantum random number generators, an enhanced ability to be able to validate or in some sense certify that those random bits really were generated randomly and freshly on the fly and weren't somehow pre-computed or pre-discovered, and potentially known by others in advance. Right? So there's these new features that quantum technologies will allow, and some of them are already deployed in real-world products. You can see you can't see it actually. It's so tiny. It's embedded in this phone, and it's already being looked at and used by customers in the financial sector, for example. Right? And it's important. Maybe I can back up a second. When I sort of drew a picture of all our digital technologies are essentially underpinned by cryptography, one of the fundamental building blocks of cryptography is the availability of secret random bits. Now, randomness has other applications as well. But one of the important applications of cybersecurity, of course, is seeding our keys, for example, in various cryptographic primitives. Now, there's another fundamental new property offered by quantum physics. With quantum physics, if you encode information in quantum bits, as you extract information about those quantum bits, you must disturb those quantum bits, right? So you can't, there's various properties that you could in principle measure, but you can't measure them all. So as you learn more about certain properties, you lose your ability to determine the other properties. And this translates into eavesdropper detectability, which is certainly a convenient thing to do if you're in the business of trying to protect your digital systems from eavesdroppers or people interfering. Of course, we can do more than just detect eavesdroppers. We can leverage that and do things such as establish keys, right? As I mentioned earlier, one of the three fundamental building blocks I highlighted at the beginning, except you can do it without relying on some sort of computational assumption, without assuming that factoring a large number is difficult, without assuming that finding a short vector in a lattice is difficult. These are so-called information theoretically secure protocols. So there is no mathematical assumption. They cannot be mathematically cryptanalyzed, right? And these building blocks have been built over actually even commercialized over the last 20 years. And we're leaving the era of short distance point-to-point quantum key distribution and moving toward long distance, even global distance quantum key distribution. And one of the enabling technologies is satellite quantum communication. So the important thing to note is that scientists and engineers, they will build a quantum internet capable of distributing quantum bits around the globe. Our job as security specialists is to figure out how are we going to leverage that new capability to better protect the foundations of our digital economy. That's our job. And again, there's tremendous programs being started and accelerated all around the world. Here's some examples in the USA, in Europe, in China. Again, tremendous progress, achieving wonderful milestones towards being able to build large-scale quantum communication networks. One of the applications of these large-scale quantum communication networks is to enable quantum cryptography. And again, our role is to figure out how to do that and when it makes sense to do that. And it'll come down to when you're designing your new cryptographic foundations. Again, these are systems that persist for decades, right? So we can't just look at where the puck is. We have to look at where the puck is going and be ready to best leverage whatever we have available to us to protect ourselves and our economy from cyber attacks of the future. And so one has to weigh the pros and cons. So if you add QKD to a particular system, it may come with an additional cost, right? It may be inconvenient because you can't achieve certain distances, at least not in the short term, but it reduces risk, right? If you use QKD alongside the so-called post-quantum algorithms. Or you could use just the post-quantum. It's a lot more convenient because you don't need, one of the wonderful things about post-quantum cryptography is you don't need quantum technology to implement it. So that's the convenient side, but it does come with additional risk. Now the amount of risk and amount of convenience, these are constantly moving and changing. So we have to track those things and also anticipate where they're going to be in 10, 15, 20 years and not unduly introduce high switching costs to migrate to a protocol that will serve us better in the medium to long term. And many players around the world are seriously looking at these trade-offs and looking how, for example, quantum key distribution or quantum random numbers can enhance their systems and their security long term. And they're doing proofs of concepts, and again, in many cases, in a growing number of cases, actually using these technologies in the field. So how do you get ready? Well, you have to go through sort of the 4 stages of quantum readiness, which is understand the technology and its varying degrees of readiness, understand how it impacts you, right? And then start planning, and lastly, implement those plans. And one can easily find quantum risk assessment frameworks, quantum risk management frameworks that you can align with your own cyber risk management frameworks and start doing those assessments and coming up based on what you discover your greatest vulnerabilities are, your highest priority vulnerabilities are, start planning your roadmap and implementing those roadmaps. You're going to need new standards, and there's great efforts worldwide. There's ETSI, of course, our friends at NIST, ISO, ITU, and so on around the world working on the standards we need to protect our digital systems. And many government players and others are starting to call for these new standards, call for these new algorithms, such as the NSA, who 5 years ago publicly declared they would be transitioning to quantum-resistant algorithms. Our friends in Germany have recently started requiring these in some of their new platforms, and others around the world as well. It's also important to note you don't have to wait until the NIST standards or other standards are done before you can start planning, right? We don't have time to do this serially in sequence. So we have a short list of candidates. We'll hear more about them throughout this workshop. And there's a relatively short list now. There's robust implementations available, open source as well as proprietary. So one can already start today testing these new tools inside your own systems to make sure they work properly. And if possible, perhaps even provide feedback to those doing the standardization efforts to make sure that the algorithms you're going to need, the performance you're going to need, is going to be available when you need it. And even QKD, or quantum cryptography, which obviously needs a new physical layer, we can start planning and preparing for that as well. There's 4 layers to quantum cryptography. There's the physical layer, and then there's network layer, and then key management, and then there's the hosts who would use quantum cryptography at the top. Those interfaces are simple and well-defined. So you can already start experimenting with what QKD could mean to your organization, how you might use it. You could, if possible, do small proof of concepts with actual hardware. Otherwise, you can simulate the hardware layer, but at the very least, prepare your architectures for QKD in the medium to long term. Another important point that is worth emphasizing, and researchers and colleagues in industry have been looking at this and advocate for this, it helps us mitigate the possibility that one key agreement method might be compromised, right? It also helps us with migration. It's a notion of hybrid key agreement. There's an equivalent for hybrid signatures, but I'll focus on key agreement here for this example. The idea is, for the shared key that you're going to use to encrypt, combine two or more key agreement methods. In this example here, I advocate, or I suggest, you could have quantum cryptography, so a key generated by quantum cryptography, combined with a key generated by your favorite post-quantum algorithm, combined with your favorite current algorithm. This gives you the best of all worlds, right? So the current algorithm probably gives you the best protection against classical attacks, because these have been around for a long time, their implementations have been studied. It gives you good protection against classical attacks, right? And then QKD and post-quantum gives you the best available protection against quantum attacks. Another advantage of this hybrid approach is that it allows you to maintain your certification and validations for the current standardized methods, and at the same time benefit from new methods that haven't yet gone through the standardization and validation process. So you get the benefits, you get the best available quantum security without compromising your certifications and your validation. Another important point to make, I typically focus on fixing the legacy systems and the legacy protocols, but we also, as we deploy new systems and new platforms, we have to evaluate them through a quantum lens as well. And even if they're not quantum safe from the beginning, there has to be a well-defined path towards making them quantum safe in due time. And again, if that's planned in from the beginning, it's probably not going to be disruptive. If it's not planned in, then it could be a major problem for everyone who's now relying on these new platforms. So I want to wrap up with pointing out that I believe this quantum threat, as we sometimes call it, is actually a blessing in disguise. The foundations of our digital system, right? We're using tools that were never designed to be the basis of everything they currently are the basis of, right? The internet was not intended to be underpinning IoT, cloud computing, financial services, and everything, right? Yet we did our best to continue to secure it sort of after the fact, but we know that if we could go back and do it all over again, we would know what to do better, right? Hindsight is 2020, so we know we could build a more robust foundation for our digital systems, but it's hard to make that case in the short term because there's so many other things to worry about. So going back and rebuilding the foundation when there's so many other challenges going on in life, we tend to never make that decision. In parallel, we just keep putting more and more value. We keep, in a sense, betting more and more, risking more and more on these fragile foundations. And we know we probably should do something about that. But again, it's not an easy thing to do. It's not an easy thing to motivate so many different players to do in coordination. So it's almost an impractical task. However, along comes the quantum threat and basically forces us to do it. Because now we have a very tangible threat, right? That will at one point, completely decimate all of our digital systems or most of our digital systems. So it's forcing us to take this long-term view, this proactive view, and now rebuild the cryptographic foundations of our cyber systems to not only reestablish the status quo, but to actually build them to be better than they've ever been and better than they would have been if we didn't have the quantum threat essentially motivating or requiring us to do so. So perhaps in hindsight, this massive exercise we're doing to make our systems quantum safe is actually better for our overall cyber immune system. So on that positive note, I'd like to stop there, and I look forward to the discussions.
Thank you, Michele. Terrific presentation. I'm I'm sure we'll pick up many of these points later today during our panel and the Q&A session with our viewers. But I do have a quick question for you now. You state the importance of planning for quantum risk management and that this must happen now. But do you think this message is getting through to sufficient business and policy leaders?
It's slowly getting through. I think it's been, the last 2 years, this message is continuing to get amplified. It's not gotten through enough yet, but it's getting there. But there's certainly a lot more to be done, partly in translating these messages in the language that would make sense to a lot of the stakeholders we need to engage, a lot of the business leaders and policymakers. I think it's very hard because obviously they're swamped with so many challenges out there. They hear the word quantum and certain preconceptions come in, and we're trying to get across the point that no, this really is something you need to worry about now. We know how to do it. We can help, but we do need your help as well, and we can do it together. So there's a lot more to be done. I don't want to say, so a lot has been done, but we don't yet have all the stakeholders lined up to take care of all the steps that are going to be needed.
Well, hopefully we can help this situation during this series of presentations we've got this week. Michele, thanks very much. We'll see you again for the panel and Q&A session later. I look forward to that. But for now, thank you very much for joining us.
Thank you.
Don't go away, as we have more still to come, including the panel discussion and live Q&A, as we've just mentioned. So please send in your questions now. Take a look at the event agenda as well for timings and details of all our forthcoming content for this 2-day virtual event. And if you missed something, don't worry, it will all be available to watch later on demand. So stay with us for our next session, but for now, thank you and goodbye.